Welcome to the CWI Deep Dive Podcast series. This is one episode in a series of 11, each covering a chapter of Welding Inspection Technology. These podcasts are designed for inspectors preparing to take the American Welding Society Certified Welding Inspector exam. They're not meant to replace enrolling in a Certified Welding Inspector preparation course or dedicated self-study, but to complement them. Along with our CWI Test Prep app available on the Apple App Store, these podcasts will help strengthen your preparation. You can continue learning at work, during your commute, or wherever you find time. Today's episode is brought to you by AMS Level 3, providing consulting, training, and compliance solutions to help companies build stronger non-destructive testing programs. Learn more at the link in the video description.
And just a reminder, this podcast is an independent educational discussion based on concepts from the American Welding Society's Welding Inspection Technology book. We are not affiliated with the American Welding Society, and this podcast is not a replacement for purchasing or studying the original text. Our goal is to provide commentary, explanations, and reinforcement to help inspectors prepare for the Certified Welding Inspector exam.
Just a quick interruption to introduce a resource to help you take your training further. The AMS Level 3 CWI Part A Test Prep app is now available on the Apple App Store. Designed for welders and inspectors preparing for the Certified Welding Inspector exam, it offers two modes. Study mode gives instant feedback with detailed explanations, and test mode simulates real exam questions with topic-based results to track your progress. All questions align with the AWS Welding Inspection Technology reference, ensuring accuracy and relevance. Download the CWI Part A Test Prep app today on the Apple App Store, and take your study time to the next level.
Okay, so today we're diving deep into Chapter 7. METAL properties and destructive testing. Our mission here isn't just, memorizing a bunch of numbers from a test report. It's about understanding what properties like strength, ductility, toughness, what they actually mean for a weld, for a structure, why they matter when you, as a CWI, sign off on something.
That's a great way to put it, because destructive testing, well, it's exactly what it sounds like. We take a sample, a specimen, and we apply a load until it breaks or fails somehow. And doing that tells us how the material behaves under stress. It gives us those critical numbers. It's fundamentally different from NDT, non-destructive testing, which we'll cover later, where you obviously want to keep the part usable. For a CWI, getting these destructive tests down cold is vital for reading things like PQRs, welder quals, material certs, all that jazz.
Right. So let's start with the big one, strength. Basically, how much load can something take? We mostly focus on tensile strength, right? Resisting a pulling force. What are the key strength values we need to know from a tensile test?
Yeah, tensile is king. And there are two main numbers. First, you've got the ultimate tensile strength, UTS. That's simply the absolute maximum load the material can handle right before it snaps, peak strength. But the second one, yield strength, is often, arguably more critical, especially for designers.
Yield strength. That's the point where things change permanently, isn't it? Like, I think of a rubber band. You stretch it a bit, let go, it snaps back. That's elastic.
Exactly. Elastic deformation. It's temporary, predictable, kind of linear on a graph. But if you pull that rubber band too hard,
it stays stretched out permanently.
Right. That's plastic deformation. You've caused a permanent change, a set. Yield strength is that dividing line. It's where the material goes from just stretching temporarily to actually changing shape for good. And think about why that matters for design. A bridge beam might not actually break if it yields.
But it's sagging. It's useless.
Precisely. It's failed its function. That's why engineers design safety factors based on the yield strength, not usually the UTS. Yield strength tells you the maximum load before the structure stops being useful.
Okay, super important distinction. Now, to get those PSI values, we have to calculate the area correctly. The chapter stresses this, and it's definitely on the exam. And it mentions the specimen needs a reduced section.
Yes, that's key. You machine the specimen down in the middle, so it's thinner there than where the machine grips it. That ensures the break happens in that controlled, measured area, not near the grips, which would mess up the results. So let's walk through the area calculation, because you got to know this. For a flat rectangular piece.
That seems easy enough. Width times thickness?
Yep. Simple as that. Say you have a plate that's 1.5 inches wide and 1/2 inch thick.
1.5 times butyl 0.5. That's 0.75 square inches.
Exactly. 0.75 inches squared. Now, what about those standard round specimens? Often see that 0.505 inch diameter figure.
Right. The 0.505. How do we find the area for that circle?
The formula is pi times the diameter squared, then divide that by 4, or pi r squared if you prefer radius. But if you plug in 0.505 inches for the diameter, it works out very conveniently to almost exactly 0.2 square inches.
0.2 square inches. I remember seeing that number pop up a lot in practice questions. It's kind of designed to make the math easier.
Pretty much, yeah. It's a common standard size. So, okay, let's use that. We have our 0.2 square inch specimen, and the test machine says it broke when the load hit, say, 12,500 pounds. How do we get the UTS in PSI?
Okay, so PSI is pounds per square inch. So load divided by area.
You got it. Load divided by the original cross-sectional area. Always the original area. So 12,500 pounds divided by 0.2 square inches.
Let's see, that comes out to 62,500 PSI.
Perfect. That's the calculation. Need to be able to do that quickly and accurately.
Now that tensile test also gives us that stress strain curve we see in the books. And the slope of the first part, the elastic part, that tells us about stiffness, modulus of elasticity.
Right. Stiffness. How much the material resists stretching elastically. Steel, for example, is incredibly stiff. Its modulus is around 30 million psi. Huge number. Compare that to aluminum, which is much less stiff, maybe around 10.5 million psi.
Big difference.
Huge. And one quick thing about finding that yield point on the curve, some metals, especially less ductile ones, don't have a really sharp, obvious knee where yielding starts.
So how do you define it then?
We use what's called the offset technique. You draw a line parallel to that initial elastic slope, but offset by a tiny amount of strain, usually 0.2%. Where that offset line crosses the stress strain curve, that's defined as the yield strength. It's a standardized way to get a consistent value when the curve is smooth.
Okay, that makes sense. A practical solution. All right, let's move from strength and stiffness to ductility. This is about how much a material can deform or stretch before it actually breaks, right? The difference between, say, a steel wire that you can bend a lot versus a piece of glass that just shatters.
Exactly. Ductile materials give you warning. They stretch and neck down. Brittle materials like cast iron or glass fail suddenly, often with little warning. And we measure ductility from that broken tensile specimen in two main ways.
Why do we do that?
First is percent elongation. You put little marks on the specimen before the test, a set distance apart, that's the gauge length. After it breaks, you put the pieces back together carefully and measure the new distance between those marks. The calculation is final length minus original length divided by original length times 100.
Okay, so if we started with 2 inches between the marks, and after breaking it measures 2.6 inches.
That's 2.6, 2.0. 2.0 equal 0.3. Multiply by 100, that's 30% elongation.
Got it. And the second way?
Percent reduction of area. You measure the original cross-sectional area, and then you measure the smallest area right at the fracture surface where it necked down. Then it's original area, final area. Original area times 100. Both percent elongation and percent reduction of area tell you how much the material can deform plastically before failure. Higher numbers mean more ductility.
Now, as inspectors often dealing with big rolled steel plates, we absolutely have to talk about directional properties. This seems crucial.
Oh, absolutely critical. When steel is rolled, the grains get elongated, stretched out in the direction of rolling. This means the material isn't the same strength and ductility in all directions. It's strongest and most ductile along the rolling direction. That's the longitudinal or X direction.
And weaker across the roll.
Significantly, you might lose, say, 30% strength and maybe even 50% ductility if you pull across the rolling direction, the transverse or Y direction. And the through thickness direction, the Z's direction, is usually the weakest and least ductile of all. So if you're doing a bend test for a welder qual and the base metal cracks, first thing you should ask is, was the specimen cut out correctly?
Right. Maybe they accidentally oriented it so they were bending across the weak direction.
Exactly. Poor orientation relative to the rolling direction is a common cause of unexpected base metal failure in bend tests.
Okay, good tip. Now let's switch gears slightly. How do we measure a material's ability to resist being dented or scratched? Hardness. And you mentioned there's a useful shortcut here for estimating strength.
Yes, with the Brunel hardness test. This one uses a fairly large indenter, usually a 10-millimeter hardened steel or tungsten carbide ball, pressed into the surface with a specific load. You need decent surface prep for it. Then you measure the diameter of the dent left behind. That measurement gives you the BHN, the Brunel hardness number. And here's the really useful part for CWIs. For typical carbon and low alloy steels, the ultimate tensile strength in PSI is approximately the BHN multiplied by 500.
Wow, okay. So a quick hardness test can give you a pretty good ballpark for the tensile strength.
A surprisingly good estimate, yeah. If the MilCert says 60,000 PSI tensile, you'd expect a BHN somewhere around 120. It's a great sanity check.
Good to know. And there are other hardness tests too, right? Like Rockwell.
Yep. Rockwell is very common. It uses a much smaller indent, either a small ball or a diamond cone, and it measures the depth of the indentation, not the diameter. It's quicker, often needs less surface prep. And then for really fine-scale work, like measuring hardness variations across a weld heat-affected zone, HAZ, you'd use micro-hardness tests. Those are typically Vickers or Knoop tests using a diamond indenter under a microscope to make tiny little indents.
Okay, so different tools for different scales. Makes sense. We'd also like to recognize Skaggs Media, LLC, as the creative force behind today's deep dive. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com.
All right, we're back. We've talked about strength under a steady load, but what about impacts or sudden loads? That brings us to toughness. Toughness is really about energy absorption. How much energy can the material take before it fractures? It's related to the total area under that stress-strain curve. But in practice, especially for structures, we're often more concerned with notch toughness. How does it behave when there's a flaw or a notch present?
And this leads right into a really critical concept, something that caused major failures historically.
Yeah.
The ductile to brittle transition temperature, DBTT. Why is this so important?
The DBTT. It's crucial because many common steels, especially ferritic steels, undergo a dramatic change in behavior as the temperature drops. Above a certain temperature range, they fail in a ductile manner, absorbing energy, deforming first. Below that range, they can fail suddenly in a brittle way like glass, almost no warning. This was a huge factor in things like the Liberty ships failing in World War II. The steel they used had a DBTT that was, unfortunately, above the cold water temperatures they were operating in sometimes.
Wow. So the cold ocean water literally made the steel brittle. That really highlights why we need a test for this. And the standard test is the Charpy V-notch.
Exactly. The Charpy V-notch impact test. It uses a very specific, standardized little bar of material. It's 55 millimeters long, 10 by 10 millimeters square cross-section. And it has a precisely machined V-shaped notch cut into one side, 2 millimeters deep, with a specific radius at the bottom, 0.25 millimeters.
Okay, very precise specimen. Then what happens?
A heavy pendulum hammer swings down, strikes the back of the specimen, and breaks it right at the notch. The machine measures how much energy the specimen absorbed during fracture, usually reported in foot-pounds or joules. Higher energy means higher toughness at that test temperature. Besides the energy value, we also often measure two other things from the broken halves.
What are those?
Lateral expansion, how much the sides of the specimen bulged out opposite the notch during fracture. More bulge means more ductile behavior. And percent shear area. You look at the fracture surface itself. A ductile fracture looks dull, fibrous, maybe gray. A brittle fracture looks bright, crystalline, granular. So we estimate the percentage of the fracture surface that looks ductile, shear, versus brittle, cleavage. Higher percent shear means better toughness.
Gotcha. Okay, so Charpy gives us energy absorbed, lateral expansion, and percent shear, all indicators of toughness, especially relating to temperature. Now let's talk about another major failure mode, fatigue. Resistance to failure under repeated loads, right? Cyclic loading. The book says something striking, that most metal failures are actually due to fatigue.
That's generally accepted, yeah. Far more failures happen because of repeated loading cycles over time, even if the load is below the yield strength, than from a single massive overload. Think about bridges, aircraft wings, rotating shafts, cycle after cycle.
How do we characterize fatigue resistance?
Usually with an SN curve. That plots stress level, S, on the vertical axis against the number of cycles to failure, N, on the horizontal axis, often on a log scale. You test multiple specimens at different stress levels and see how many cycles they last before breaking. What's interesting is that for steels, the curve often flattens out at lower stress levels.
What does that flattening mean?
That's called the endurance limit or fatigue limit. It suggests there's a stress level below which the steel can theoretically withstand an infinite number of cycles without failing. But, and this is important, not all materials have this. Aluminum alloys, for example, typically don't have a true endurance limit. Their SN curve keeps trending downwards. That means even at very low stresses, given enough cycles, an aluminum part is expected to eventually fail by fatigue.
That's a critical difference for design and inspection. And this really brings inspection to the forefront, doesn't it? Because fatigue failures are super sensitive to surface condition, stress risers.
Absolutely. Hugely sensitive. Fatigue cracks almost always start at some kind of stress concentration. And where do we find stress concentrations in welds? Surface discontinuities. Things like undercut at the toe of the weld, sharp corners from excessive reinforcement, overlap, even just rough weld ripples, they all act like little notches.
So they magnify the stress right at that spot.
Exponentially. That little notch becomes the perfect place for a tiny fatigue crack to start. And once it starts, each load cycle makes it grow a little bit until eventually the remaining material can't take the load and bang, failure. That's why, generally speaking, surface flaws are a much bigger worry for fatigue than internal flaws like porosity or slag, just because the stresses are usually highest right at the surface.
Okay, so vigilant surface inspection is key for preventing fatigue. Good connection. Let's move now to the destructive test that CWIs see all the time for procedure and welder qualification, the soundness tests.
Right, these are the bread and butter tests. The most common one for qualifying welders is definitely the bend test. We cut specimens transversely across the weld. Depending on the test, we bend them different ways. Face bends put the top surface, the weld face, in tension. Root bends put the bottom, the root side, in tension. And for thicker materials, we often use side bends, where we cut the specimen so the actual cross-section of the weld gets bent and stretched.
And the process is basically forcing the specimen into a U-shape around a jig, a 180-degree bend.
Yep, using a guided bend jig with a specific radius plunger and die. You force it into that U-shape. Then you examine the surface that was stretched, the tension surface.
And what are you looking for? What makes it pass or fail?
You're looking for discontinuities that open up on that surface, things like cracks, lack of fusion, big pores. Most codes, like AWSD 1.1, have limits. Usually any single flaw can't be bigger than 18-inch in its greatest dimension. There might also be limits on the total number or sum of smaller flaws.
Okay, so visual inspection of the bent surface against code criteria. What about the nick break test? See that a lot in pipeline standards like API 1104.
Yeah, the nick break is a bit different. Its purpose is specifically to let you look inside the weld. You intentionally cut notches or saw cuts into the edges of the weld, usually near the center. Then you literally break the specimen apart, forcing the fracture to happen through the weld metal.
So you're creating a fracture surface to examine.
Exactly. You examine that broken surface visually. You're looking for internal imperfections, trapped slag, porosity, maybe incomplete fusion that didn't show up on the outside. Acceptance is based on the size and distribution of those flaws on the fracture face. API 1104, for instance, has very specific limits, like maybe no slag inclusion deeper than 132-inch.
Got it. A forced fracture for an internal view. And the last main one is the fillet break test. Remember, pronounce it fillet.
Right. The fillet weld break test. This one's often required for qualifying tack welders, say under D 1.1, and sometimes for procedure qualification for fillet welds. You basically set up the fillet welded T-joint specimen and apply a load to peel one plate away from the other, breaking the fillet weld.
And what determines acceptance there?
Again, you examine the fracture surface. The main things are checking for complete fusion, especially down to the root of the joint. You don't want to see unfused areas. And you also check for porosity. Typically, the code might say any single pore can't be larger than 332-inch in its greatest dimension. It's a pretty straightforward visual check of the fillet quality.
Okay, those three bends, nick breaks, fillet breaks seem like core practical tests for the CWI. Now, we talked a lot about mechanical properties. Let's take a step back and connect them to the underlying chemistry. Why does the material behave the way it does?
Yeah, the chemistry is the root cause, isn't it? The absolute most important element in steel is carbon. Adding even small amounts of carbon makes steel harder and stronger. That sounds good, right?
Seems like it.
But it comes at a cost. Carbon drastically reduces weldability and ductility, makes the steel more prone to cracking, especially in the heat-affected zone. That's why most structural steels that we consider easily weldable have pretty low carbon content, usually well under 0.5%, often much lower. High carbon means high risk in welding. As an inspector, seeing high carbon should immediately raise red flags about needing proper procedures, maybe preheat.
And that's why we have things like the carbon equivalent formula, right? To account for other elements that also add hardness, mimicking carbon.
Exactly, because it's not just carbon. Manganese, chromium, molybdenum, vanadium, they all contribute to hardenability too. The CE formula tries to lump their effects together to predict weldability. Then you have the bad actors, usually impurities. sulfur and phosphorus. Generally, you want these as low as possible. They both tend to make steel brittle, especially phosphorus causing temper embrittlement and sulfur leading to hot shortness or cracking during solidification. Though sometimes sulfur is added intentionally in small amounts to make free machining steels. Easier to cut, but
Terrible to weld.
absolutely terrible to weld. Generally avoid welding free machining steels if you can help it.
Warning. And then there's chromium, the key ingredient for stainless steel.
Right. Chromium is the magic element for corrosion resistance. You need at least about 12% chromium to officially call a steel stainless. It forms that passive chromium oxide layer on the surface that protects it.
And that leads to all the different types of stainless steel, which the CWI needs to be aware of.
Definitely. There are 5 main families: austenitic, like your common 304 or 316, martensitic, hardenable, like 410, ferritic, like 430, magnetic, precipitation hardening, like 17 to 4 pH, and the duplex grades, a mix of austenite and ferrite. You gotta know the family because they behave very differently during welding. Austenitics are prone to distortion and sensitization. Martensitics often need significant preheat and post-weld heat treatment. Ferritics can have toughness issues. Duplex needs careful heat input control. The inspection approach changes depending on the type.
Okay, so knowing the stainless family is crucial. Finally, let's touch on metallographic testing, getting that close-up look at the structure. 2 levels here.
Yeah, basically 2 scales. First is macroscopic examination, or just macro. This is low magnification, usually 10x or less, sometimes even just with the naked eye after etching. Macros are great for looking at the overall weld profile. You can check for fusion depth, penetration, see the number of passes, measure fillet weld legs and throats, check for big cracks or porosity. It gives you the big picture of the joint geometry and general soundness.
Okay, the overview check and the detailed view.
That's microscopic examination, or micro. Now we're talking high magnification, 100x, 500x, even higher. This is where you identify the actual microstructural constituents: ferrite, pearlite, martensite, austenite grains. You look for tiny defects, micro cracks, analyze inclusions, or investigate failures in detail. And for both macro and micro, you almost always need to etch the polished sample first.
Etching, what's that do?
You apply a mild acid or chemical solution. It selectively attacks the different phases or green boundaries in the metal at different rates. That difference in attack reveals the structure, makes the grain boundaries visible, shows different phases and different shades. Without etching, a polished metal surface often just looks like a mirror. Etching brings out the detail.
Got it. So etching is key to seeing the structure. Wow, we've covered a lot today, from understanding yield strength and why it matters more than UTS for design, all the way to how chromium makes steel stainless and why etching is needed for metallography. Really, understanding these properties and tests isn't just about passing the CWI exam. It's about being able to look at a test report or a material cert and know what those numbers mean for the safety and reliability of the structure you're inspecting. It connects the lab results to the real world.
Couldn't agree more. And maybe a final thought to leave folks with. We spent all this time talking about the methods, tensile testing, Charpy, hardness, bends, and the results they give us. But think about this. How absolutely critical is the specimen preparation for every single one of these tests? A poorly machined tensile bar with the tool mark in the reduced section. A Charpy notch with the wrong radius or depth. A hardness test on a rough or decarburized surface. A bend specimen with saw cuts left on the corners. Any tiny flaw in the preparation can completely throw off the results. It can make a perfectly good material look bad, or worse, maybe make a marginal material look acceptable. So, while the test method is important, ensuring the specimen itself is prepared meticulously, exactly according to the standard, that's arguably just as critical. That preparation is part of the inspection process. Get that wrong, and the numbers don't mean much. Something to keep in mind. Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training and mentorship, or compliance solutions like NADCAP and Federal Aviation Administration readiness.
If you've made it this far in the podcast, I'd like to ask for your support. Please consider buying us a coffee. Your contributions help cover the monthly subscriptions we use to produce these NDT training videos and keep new content coming. We offer 3 levels of support. NDT Level 1, $1 per month, NDT Level 2, $2 per month, and NDT Level 3, $3 per month, or a one-time gift of your choosing. Just scan the QR code on the screen to join and help us continue delivering updated NDT resources right here on YouTube. At AMS Level 3, our mission is to strengthen technicians and companies through consulting, training, and compliance solutions. Subscribe to our channel for more mentoring insights, share this video with your team, and give it a like to help spread the word. Visit us at amsl3.com to learn more about our services and resources designed for NDT professionals at every level. And a special thank you to Skaggs Media, the creative force behind these videos. Learn more at skaggsmedia.com.